Hello U12s and welcome back to mathematics. In today's lesson we're continuing with our topic of sequences and series, and we're going to be talking about a thing called a limiting sum. Now in the last lesson we talked about a geometric series, and in a geometric series this is when we are adding up the terms in a geometric sequence, and so the sum for a geometric series is a times r to the power n minus 1 over r minus 1. And so we use that in a few different questions, and in the online lesson we actually went through a few more examples of this. What we're doing here is we're looking at a particular case of a geometric series, and in order for us to actually get an idea of why this particular case happens, we have this example here. So this is called a limiting sum, and let's just have a think about this question here. A frog is about to jump over a river that is 10 meters wide. The first jump it can make is 5 meters, where there will be an object to help it stay above water, and each subsequent jump it can only jump half as much as the previous jump. Will the frog get across the river by jumping? So what we're imagining here is that there is a 10-meter river, and there's a few rocks in between in this 10-meter river, and we've got a little frog here, and the frog has got froggy eyes there, and it's doing ribbit. We've got a frog, and it's trying to jump across this river. And so the first jump that it makes, it goes halfway, roughly about here, I believe, to 5 meters. And so it jumps to 5 meters, and then it follows this pattern where each following jump is just going to be as half as long as the previous one. So for example, the next jump will be at, if we halve 5, that would become 2.5, which is, when I add that on top, we'll get it to 7.5. So I've jumped 5 meters, so this is a 5-meter jump. We've jumped 2.5 meters in the second one, and we keep repeating this process. And so the next jump will be what happens here? It'll be at 8.75, because we halve again, and we jump 1.25 meters. And this pattern continues. Now, if you think about this pattern, well, if this keeps continuing into infinity, all the way to, as it keeps repeating itself, what will happen? Well, as the distance gets smaller and smaller, well, we've covered all of this distance here. But as we get towards this end, and at any point, well, there's still a small distance between whatever rock we're up to and the next, and getting to 10. And so we can keep halving that. But whenever you keep halving that distance, the distance doesn't actually ever disappear if we keep repeating this. Because I can just, once I halve it again, so when I add the next one, which is, I think 0.675. So 0.675, and I add that on top, I'll actually get a 9.425, and then even here you've still got a small little distance, and each subsequent jump we're only halving that, but this process of halving doesn't ever get rid of that distance. And so even if we keep repeating this all the way into infinity, if you think about this, there's still going to be a small distance. But that doesn't make any sense. We can see, it's hang on, if we keep just doing this, it should eventually reach 10. It just doesn't make any sense. The frog doesn't actually reach the other side. And this is actually a fairly famous paradox called Zeno's paradox, where Zeno is this Greek philosopher, and he basically said, well, in order for me to get from between any two positions, well, I need to make my way halfway there, and then from there I need to go halfway there, and then from here I need to go halfway there, and we don't actually. And here the whole paradox was going, well, I end up reaching my final destination, but if I think about it, we've actually figured out how to sum up to infinity. And so this is actually one of those big paradoxes. In the maths course, what we actually call this is a limiting sum. There's actually a value that if we do this pattern continually until infinity, there should be a value that it eventually reaches. In this case, for this example, the frog will eventually reach 10 meters. Eventually, after if we've got sum this all the way to infinity, it should just add up to 10. And so this is what a limiting sum is. A limiting sum, and there's a particular condition for it. A geometric series will converge to a limit. So this is what it's called, why it's called a limiting sum. It will go towards this particular value or limit, and it's called a limiting sum. And this is only in the case if our common ratio is between the following values, 1 or -1. Or the shorthand way of doing this is, the other way that we could write this is the absolute value of r is less than 1. And so for a geometric series, if the common ratio is between 1 and -1, so it's like a fraction value that is between 1 and -1, that will actually result in a limiting sum. So if we added all those terms up to infinity, it will end up actually getting a specific 1 value. Okay. So here, the sum of a geometric series. The reason why this particular formula happens is the sum of a geometric series, which we said at the beginning, was a times r to the power n minus 1 over r minus 1. And so if the common ratio r, and actually here we're going to use the other form, we'll explain why in a moment. So here we're going to have a times 1 minus r to the power n over 1 minus r. So what we have here is if r is, if the absolute value of r is less than 1, so it's between those values of 1 and -1, then this term up here is going to be greater than 0. And if we take the limit as n goes to infinity, what will happen is, well, if we keep, so let's say we have a number which is small, between 1 and -1. So let's say like 0.5. If I raise that number to the power, to a very big power, so let's say I raise it to the power of 2, notice the number is getting smaller and smaller and smaller. And so it actually gets smaller. So if I keep raising that to like higher powers, it gets smaller. And if I raised 0.5 to the power like 100 or 1,000,000, it says that we'll get to 0 eventually. Well, because the calculator doesn't want to bother calculating that. Oh, it's actually already at 1,000. It's already got 0. Let's do 100. Yeah, there we go. The number gets really, really, really small. And so what happens here is the sum as n goes to infinity, what will happen is that this r to the power n term will disappear. So we get a times 1 minus 0 over 1 minus r. And so we get this result here. So the formula that we're actually going to use is that when we take this infinite sum, we're going to get a over 1 minus r. So this is only when, so let me erase this. This is only when the absolute value of r is less than 1. And so this is a formula that we're going to use for this infinite limiting sum. If we have a geometric sequence or geometric series, and the common ratio is less than 1, or actually between 1 and -1, or the absolute value is less than 1, then it's going to have this limiting sum. Okay, so let's have a go at a couple of examples of this. First part, example 35. Explain why 2 plus root 2 plus 1 has a limiting sum, and find the sum. Okay, so if we want to show something has a limiting sum, what we need to do is just show that the common ratio fits that criteria. The absolute value of that common ratio is less than 1. So let's actually figure out what the common ratio is. With the common ratio, when we're dealing with geometric series, what we do is we take 2 consecutive terms and we divide it. And so here we get, let's pick any 2 consecutive terms. You can pick any 2 here. I'm going to pick this one here, like 1 and root 2. So the common ratio is just going to be 1 over root 2. Now we can chuck this in the calculator. 1 over square root 2. And we get 0.707, which is less than 1. So here, therefore, absolute value of r is less than 1, and so a limiting sum exists. So the condition for us to have a limiting sum is that if we have a geometric sequence, so here we have, this is a geometric sequence, and the common ratio is less than 1. So we've got a geometric series. Actually, I should have probably tested that this was actually a geometric series sequence. We'll actually, maybe in the online lesson we'll go back on that. But here we've got a geometric sequence, and so and that common ratio is less than 1. Okay. Oh, the absolute value is less than 1, I mean. Okay, the next part is we also want to find the sum. And so the way that we do this is we're going to use this formula. The infinite sum is equal to a over 1 minus r. So a is just the starting term, r is the common ratio. And so here, also the additional thing to note is that this formula is on your reference sheet, so you don't need to remember it. As long as you just need to find it in the section with sequences and series, and you should be okay. Okay, so what I'm going to do is I'm just going to substitute my values. A, the starting term was a 2, over 1 minus the common ratio 1 over root 2. Now here, if you have a look at the answer, we want to just simplify that. So we're going to do a little bit of algebra to help me, a little bit of, not algebra, a little bit of just manipulation of this expression to help me find that value. So here I'm going to just fix the bottom, make it into a common denominator. So I get 2 over root 2 minus 1 over root 2. And when I divide by a fraction, when I divide by a fraction, I just flip it and multiply it. So I multiply to get the reciprocal, multiply by the reciprocal. I'm going to keep moving over here. I apologize, it's going across. And so here we get 2 root 2 over root 2 minus 1. We want to then from here rationalize the denominator. So we don't want any square roots at the bottom. So here I'm going to multiply top and bottom by root 2 plus 1. Root 2 plus 1. And so here we can, what we get at the top is 2 root 2 over root 2 times root 2 plus 1. At the bottom, it'll become a difference of 2 squares, and we end up getting 2 minus 1, which is just 1. And continuing here, we get, when we expand out the brackets at the top, we get 4 plus 2 root 2, which is the answer that we have here. So that one was just a bit of manipulation of the terms there. Okay. So that is how we can find the limiting sum. The limiting sum, we have to check the condition that the common ratio is less than, the absolute value of the common ratio is less than 1. And then once we do that, all we need to do is just throw our starting term and that common ratio into the formula. Okay, let's have a look at the next example. Kevin has started an exercise program to lose weight. When he started the program, he weighed 105 kilos, and in the first month, he lost 5 kilos. In the second month, he lost 4 kilos. In the third month, he lost 3.2 kilos. And in the third month, he lost 3.2 kilos. If this weight loss trend continues, well, actually, before we continue, let's have a look. Okay, what kind of pattern do we notice here? So when you look at this, what indicates to you that this is going to be a geometric progression in particular? Well, if you have a look, we've got this pattern here of 5, 4, and 3.2. And if you have a look at how much it goes in between each one of them, you're thinking to yourself, well, 5 to 4, that means he lost, the difference in the amount that he lost in the first and second month is he's lost 1 kilo less. And then the 4.2 to 3.2, that's 0.8. And so that's not a common difference each time. And so that to me indicates, oh, actually, this might have to deal with a common ratio. So let's have a look at the questions. If this weight loss trend continues, how much will Kevin lose in the 4th month? So here, what we want to do is actually figure out how much he's losing in that 4th month. What we're doing is we're finding a term in a geometric sequence. So here, I'm going to just write the formula. T n is equal to ARN minus 1. And so here, if we have a look, we want to find how much he loses in the 4th month. So I want to find T4. Now, let's just put in our values here. So A is just a starting month, which is 5 times R. Now, we haven't figured out what R is. Let's just do that working out on the side. R is just if I take any 2 consecutive turns in my sequence. And so here I've got, let's take 4 and 5, and I just take the 2 and divide it. So 4 over 5. Great. So 4 over 5, or to the power 4 minus 1, or 3. And we can chuck this in the calculator. 5 times 4 over 5, and I'm going to just make sure I put a bracket there just to make sure I get there, to the power of 3, and we get, he loses 2.56 kilograms in the 4th month. Okay, that's what we have here. So this one, we actually wanted to find the term of the 4th month for this geometric sequence. Okay, the second part. What will be his ultimate weight? Now, if you have a look at this, his ultimate weight is just basically what will happen if he continues this weight loss pattern, and eventually goes, we reach a target, like a specific weight that he will get. Now, if you have a look at the previous part, we had a common ratio of 4 over 5. 4 over 5 happens to be less than 1 and fits that criteria of absolute value R being less than 1. So that means that when I see that particular condition, if I see that common ratio being less than 1, that to me tells me, actually I need to use a limiting sum. So I'm going to use that limiting sum formula. So s to infinity is equal to a over 1 minus r. And so that tells me that I need to put in the value. So a was 5 kilos. He started off with losing 5 kilos in the first month. And we've got 1 minus the common ratio of 4 over 5. And so if you put this in a calculator, I believe this gives you 25. Okay, now, if you think about this, does this tell us that Kevin is going to eventually weigh 25 kilograms? Well, not quite, because all of these numbers that we have here in this sequence, this is how much weight he has lost. So in the first month, he lost 5 kilograms. In the second month, he lost 4 kilograms. In the third month, he lost 3.5 kilograms. In the fourth month, he lost 2.56 kilograms. This is not how much this is not how much he weighs. This is how much weight he has lost. And so if I want to find Kevin's weight, that's just going to be whatever his starting weight was minus this amount that he lost. And so if you have a look in the question, he started off as 105 kilograms. And so Kevin's weight is just going to be 105 minus 25, which tells me he's going to end up weighing 80 kilograms. That's his ultimate weight. Okay, so that's another example where we can use our limiting sum. And once again, when you see a common ratio of a geometric series being less than 1, that should indicate to you, hey, I actually need to use the limiting sum formula as opposed to my regular formula. Okay, let's have a look at this next question. I think I'm skipping over this one. Yes, I'm skipping over this one. Extension 1. Extension 1, boys. We might go through that one. Okay, example 38. So here we want to consider the following series. Sine squared x plus sine to the power 4x plus sine to the power 6x plus and so on for x being between 0 and pi. Now, let's just talk about a few things. We've got a trig ratio sine, and here they've also limited our domain to be sine x is between 0 and pi over 2. Now, if you think about your quadrants, x is between 0 and pi over 2 is just this between 0 and pi over 2. So we are in our first quadrant, the OR quadrant, where all of our trig ratios are positive. So what this means is that all of these values are going to be positive because we're in the first quadrant. Sine is always positive in the first quadrant, or all our trig ratios are going to be positive. So that means that if I square a positive number, if I cube a positive number, if I raise a positive number to a power 4, all of these values are going to be, greater than 0. The other thing is, well, sine in between 0 and pi over 2. So if I draw my sine graph, sine looks something like this. And so 0 to pi over 2 is just between 0 and 90 degrees. And here, this is pi over 2. So the values of sine, if you have a look, between 0 and pi over 2, well, that's actually between. So sine x is going to be between 0 and 1 when we're between 0 and pi over 2. So just by reading this question, these are 2 pieces of information that I can pull out just based off of this domain restriction. The domain restriction just means that we're in the first quadrant, so sine is positive. And the second thing is, if you look at the sine graph, where the values of sine are going to be between 0 and 1. So let's have a look at the first part. Part 1. Show that a limiting sum exists. Okay, well, if we want to show that a limiting sum exists, there's actually what we want to do is just check that the common ratio is the absolute value of the common ratio is less than 1. Now, if you have a look at the question, the other thing that I said earlier was that you might want to also check that it is, firstly, show that is a geometric series. But if you have a look, this is 1 marker. I would probably just, that to me indicates that we're probably just going to need to check the common ratio. So let's have a look at that. So the common ratio, let's find the common ratio. I take any 2 consecutive terms, so let's take the second term and the first term. So I'm going to have sine to the power 4x over sine squared x. So here I can simplify this. Well, I've got sine to the power 4 divided by sine to the power 2. And so these powers will cancel out. So this will cancel out and I'm left with a power 2. And so here, the common ratio is sine squared x. I'm multiplying by sine squared x to get to the next term. Okay, from this, how can we find the limiting sum? Well, how can we show that this is a limiting sum? Well, we want to show that sine squared x is actually less than 1, or absolute value of sine squared x is less than 1. Now, what we said was, sine x, because we have this domain restriction, this is actually between 0 and 1 anyway, because of the sine graph. So here, I'm going to write here, if sine x is between 0 and 1, for x is between 0 and pi over 2. So here, that was just based on our domain. So when x is between 0 and pi over 2, so 90 degrees, and sine x is just going to be between 0 and 1 anyway. So if we square those values, so if I square sine x, what's going to happen? Well, it's still going to be between 0 and 1. So that tells me that sine squared x is going to be less than 1 over that domain. So that means that the absolute value of r is going to be less than 1. Our common ratio is going to be less than 1. Okay, so that means, therefore, a limiting sum exists. So here, the important thing was the fact that our common ratio, the absolute value of our common ratio was less than 1. Okay, so I've shown that the limiting sum exists. If the common ratio, absolute value of the common ratio is less than 1, that means a limiting sum exists. Okay, part 2, find the limiting sum. This part, all we need to do is just chuck in that formula. It's a over 1 minus r formula. So here, let's just substitute a few values. At the top, we've got a, which is our first term. So our first term is sine squared x over, at the bottom, I'm just going to write 1 minus, r is our common ratio, and in this case, our common ratio also happens to be sine squared x. Okay, we want to simplify this, write this in simplest form. So we've substituted all our values in, that's great. But here, we want to put it in simplest form, and this is the part where this is a 2-mark question. If you have a look, we've just substituted. That's probably worth just the first mark. What we want to do is actually rewrite this in simplest form. Now here, this is where we need to use a bit of our knowledge about trig. Sine squared x, or anything squared. Sine squared, cos squared, tan squared. When you see that sine squared, there's actually one of our identities on our formula sheet that we can use here. So what we can actually use is, if you remember, on our formula sheet, there's a trig identity which says that cos squared x plus sine squared x is equal to 1. Now if you have a look, I've got sine squared x on the top, I've got sine squared x at the bottom. So what I can do here is I can actually rearrange this guy here to make if you have a look, I want 1 minus sine squared x. So what I can do is I can move this to the other side. And so here I've got cos squared x is equal to 1 minus sine squared x. So what I can do is, well, I've got 1 minus sine squared x right here. So I can just replace it with cos squared x, because this identity just tells me that those two are equal. So this just becomes sine squared x over cos squared x. Okay, that's one step. Great. Can I simplify this any further? Well, here, this is where we're going to need to use another trig identity. Well, here, if you have a look at the top, we've got sine x, and at the bottom, we've got cos x, and it happens to have the same power. Sine over cos just becomes tan, and so this final answer is just going to give me tan squared x. Okay, so that's how we do this particular question. So once again, limiting sum, absolute value of our common ratio is less than 1. And here, what we actually needed to do was apply a bit of our knowledge from trig to actually help me simplify this. Okay, and the last one is actually us working backwards. So if you have a look here, find the value of x if the sum from n is equal to 0 to infinity of 9 over x to the power n plus 1 is equal to 18. Now this one, you might be looking at it and going, hey, this doesn't look anything like any of the previous questions that we looked at. There's a few bits in this question that I'm going to actually help break down just to help you see how it's actually the same. Now let's first start off with this sigma notation. Now here, we're taking the sum of all the terms from n is equal to 0 all the way to infinity. If you think about what we said the limiting sum was if I added up all of the terms in my sequence to of a particular geometric sequence where the common ratio was less than 1. So we're adding to infinity. So this is just another way of someone sneakily writing that we're dealing with a limiting sum. Okay, so what they're telling me is that we're taking the limiting sum of this particular pattern. So let's just actually figure out what's happening here. Well, if you remember, well, actually, before I do that, what we want to actually do is we want to use, because we see it's a limiting sum, we want to use that formula, S infinity is equal to A over 1 minus R. So what we want to do is we want to find our starting term and also that common ratio. And what we need to do in order to do that is play around with this guy in here. Now, the starting term, very simple. What's our starting term? Well, we're starting from n is equal to 0. So A is just going to be what happens when we sub in 0 into this particular into this formula here. So I'm going to get 9 over x to the power 0 plus 1. So we're going to get 9 over x. Okay, so I've got my starting term A. Now, what we want to do now is find that common ratio. Now, what do I need to do to find a common ratio? Well, let's just think about what this sum is. This sum is actually telling me I'm going to add from n is equal to 0 all the way to infinity. So let's actually write out a bit of this sum. So if I write out a bit of this sum of from the sigma notation, when my pen decides to work, there we go. Well, we figured out that the first term is n over. Okay, cool. Then the next term is, what's going to be the next term? Well, the next term is when I sub in n is equal to 1. So I'm going to get 9 over x squared for the next term because I sub in 1 into n. And so I got x to the power 1 plus 1, which is 2. Plus, third term is just going to be when I sub in n is equal to 2 in this particular case. And it's going to be 9 over x cubed plus, and so on. Now what we want to do is we want to find that common ratio. So if you have a look here, what I need to do is I pick any two consecutive terms and I just divide them. And so here for this one, I'm going to get r is equal to 9 over x squared divided by 9 over x. Now when I divide by fraction, once again we just flip it. And so here, and we got and multiply. So we've got 9 over x squared times x over 9. And so here I can start to cancel out a few things. So the 9's cancel, and x will cancel out x squared and leave me with an x. And so here I have a common ratio of 1 over x. Okay, so what we want to deal with here is that because we've got this limiting sum, we figured out this common ratio. Now, what we want to, with that common ratio, we want to say that it's less than, the absolute value of this common ratio is less than 1. But if you have a look here, that doesn't actually help me do very much. It just tells me that x is going to be less than, going to be, in this case, it's going to be greater than 1, which isn't very helpful for me at the moment. But if you have a look, this limiting sum, if you have a look at what the question tells me, it tells me that this is equal to 18. So what I can do is I can put in my value of a and r into my limiting sum formula and just solve it being equal to 18. So that's what we're going to do. Let's do that. So the limiting sum formula was s infinity. The limiting sum is equal to a over 1 minus r. From the question, they tell me that the limiting sum is equal to 18. And so that's going to be equal to a, 9 over x, over 1 over x, which is our common ratio that we just found. Okay, at this point, we just need to do a little bit of algebra to help me solve this. Now, what I'm going to do, I've got a fraction over here. I'm just going to multiply that over to the other side. So I've got 18, 1 minus 1 over x is equal to 9 over x. And I can expand out my brackets. So I've got 18 minus 18 over x is equal to 9 over x. Notice we've got these terms which we have over x with the same denominator. So I'm going to move them all to the right-hand side to make it easier. So I've got 18 is equal to, when I add those two together, I'm going to get 27 over x. Multiply the x over 18, x is equal to 27. And so x is going to equal to 27 over 18, which is 3 over 2. And so here, this is actually us working backwards to find that common ratio given the limiting sum. So here we got given the limiting sum value. We got told that when we added this together, it was going to equal to 18. And we actually worked backwards to find that what the common ratio, or what the value of x was. Okay, so that's it for today's lesson. Let's just do a quick summary of what we did today. So today we talked about what a limiting sum was. A limiting sum is when we have a geometric series and the common ratio is between those values of -1 and 1, or the absolute value is less than 1. And so what happens is when we take this limiting sum, so when we sum all the terms up to infinity, it will give me a particular value. And so this is similar to that Zeno's paradox that we went through with the frog, or like just where we kept halving the distances and noticing that, well, even if we make the distances smaller, it's eventually going to eventually reach the same point. We went through a few examples of this and how we can apply this limiting sum formula and solved a few different problems with that. So that's it for today's lesson, Year 12. If you have any questions, feel free to email me or send me a message. I'm Google Classroom, more than happy to try and answer your questions. But as always, stay safe, stay healthy, stay wonderful, and I'll see you on our online lesson. Bye.